Welcome to This Explainer. Today, we're diving into something totally fascinating. We're exploring machine learning for Raga analysis and discovering exactly how artificial intelligence is stepping in as a sort of digital detective to decode the ancient, deeply emotional structures of Indian classical music. Let's just jump right in.
So here's the ultimate mystery we are investigating today. How can computers possibly uncover hidden mathematical rules in music that to us sounds entirely free-flowing and boundless? When you listen to a skilled musician perform a raga, it feels incredibly spontaneous, right? The artist is improvising, they're bending notes, reacting to the moment. It feels like pure emotion, totally unconstrained by rigid rules. So, how can a machine, something that relies entirely on strict logic, discrete numbers, and predictable patterns, make sense of something so incredibly fluid?
Well, to understand the challenge here, we really have to look at how different musical systems operate. Think about Western classical music for a second. It's kind of like stepping up a very distinct staircase. The notes are discrete, they're fixed, right there on a page of sheet music, and they are played exactly as written. And, traditional audio analysis tools were built specifically for this staircase. But Indian ragas and Ottoman Turkish makams, they are entirely different beasts. They're much more like sliding smoothly up a ramp. Musicians constantly use continuous glides, microtones, and heavy improvisation between the actual notes. Because there aren't these clear, hard boundaries between the pitches, traditional Western music analysis completely fails to capture what's actually happening in the performance.
To the untrained ear, the opening improvisational section of a raga, which is called the alap, sounds completely spontaneous. There's no fixed rhythm, no percussion, it's just the artist freely exploring the melody. But data science reveals a completely different reality. The alap is actually strictly governed by this invisible acoustic grammar. The artist isn't just wandering randomly. They are operating within a highly complex, rule-based framework that dictates exactly which notes to emphasize, which notes to glide through, and precisely how to transition between them. So it's unstructured on the surface, but mathematically rigid at its core.
Since standard sheet music can't possibly capture these microglides and improvisations, researchers have turned to a really fascinating field of computer science called music information retrieval, or MIR for short. Instead of trying to read a static score, MIR algorithms extract raw audio waveforms directly from concert recordings. They process the actual physical sound, the complex vibrations hitting the microphone, and effectively pull the acoustic fingerprints right off the music. This lets data scientists analyze the living, breathing performance itself.
Okay, so to make sense of all that continuous sliding and gliding, researchers use a really clever tool called pitch class distribution, or PCD. A PCD is essentially just a statistical histogram. It maps out exactly how often specific pitches are played over the course of a whole performance. So even though the audio is this continuous rolling series of peaks and valleys, the PCD aggregates all that data to reveal the foundational notes hiding beneath the improvisation. It basically creates a unique visual fingerprint for a specific raga or makam, showing us exactly where the musician chose to spend the most time.
Now, while the basic histogram is great for showing us what notes were played, researchers actually solve the problem of analyzing those continuous glides using something called time-delayed melody surfaces, or TDMS. And what TDMS does is it adds the crucial dimension of time. It tracks exactly how a musician slides from one specific note to another. It captures the temporal transitions, essentially the journey between the musical destinations. And that is absolutely vital for identifying the true character of a makam or raga.
By leveraging these advanced MIR tools, the algorithms are basically acting like digital detectives. They sift through massive amounts of audio data to find the fundamental anchors of a raga's unique identity. Now, in Indian classical music theory, these foundational anchors are known as the Vadi, which is the king note, and the Samvadi, the queen note. These are the tonal centers of gravity that the entire improvisation orbits around. But the real question is, can a machine actually prove that these king and queen notes exist just by crunching the raw audio data?
Well, the proof is right here in the numbers. The algorithms prove that despite the intense, free-flowing improvisation of the alap, musicians are mathematically holding these king and queen notes significantly longer than the standard notes. The machine isn't being spoon-fed the rules of the raga, it is discovering them purely through the statistical duration of the pitches. It literally validates the ancient acoustic grammar, proving that the concept of Vadi and Samvadi isn't just some nice theoretical idea, but a measurable physical reality in the performance itself.
And this actually brings us to a massive philosophical shift in data science that's highlighted in the sources.
In the past, the goal of a machine learning model was simply to achieve a high accuracy score, like getting a computer to correctly label a raga 95% of the time and calling it a day. But the new paradigm focuses on the task. It's about moving away from just chasing a high score and actually trying to understand the deep cultural grammar of the music. Why did the machine get it right? Or, honestly, more importantly, why did it get it wrong? By focusing on the task, researchers are using unsupervised learning to explore the really subtle nuances of tuning, intonation, and melodic similarity.
Let's put this deep understanding to the test with a really fascinating musical mystery. Raga Bhupali and Raga Deskar are notoriously difficult for students to learn because they share the exact same 5 pentatonic notes. They literally have the identical scale. If you just look at a basic list of the notes being played, they look exactly the same. So how on earth does an algorithm tell them apart? If it's not the notes themselves, what hidden variable is the machine actually detecting?
Are you ready for the answer? It's 25 cents. And no, obviously not the money. In acoustic terms, a cent is a microscopic unit of pitch. The algorithm successfully discriminates between these two identical scales by detecting a tiny microtonal difference of just 25 cents in the intonation of the ga note. In Raga Deskar, the musician sings that specific note just a fraction of a hair sharper than in Raga Bhupali. The machine picks up on this incredibly subtle tuning difference, a difference so small it represents the unwritten, stylistic knowledge passed down directly from teacher to student. It's wild.
All right, let's pivot a bit to our next massive revelation and see how all of this builds into human emotion. We've seen how machines decode the math, but what about the feeling? For about 2,000 years, the ancient Raga Rasa theory has claimed that specific musical configurations trigger distinct, predictable neuro-emotional responses in the listener, known as rasas. It suggests that music isn't just subjective art, but a targeted emotional catalyst. And today, modern science is putting this ancient claim to the ultimate test.
You know that feeling when a song literally gives you chills, or makes you feel instantly relaxed, or suddenly highly focused? Well, researchers are now quantifying that exact feeling. By pairing real-time EEG brainwave monitors with BioWell energy scanners, scientists are tracking human neurobiology while people listen to ragas. They then feed this massive amount of biological data into artificial neural networks, which are advanced computing systems inspired by the human brain that excel at finding hidden, nonlinear patterns.
And it maps out beautifully. The neural networks found direct, highly predictable correlations between specific ragas and human brainwave states. For instance, listening to Raga Hamswani distinctly boosts beta waves, which are responsible for cognitive clarity and mental focus. On the other hand, Raga Shankar Bharanam elevates alpha waves, stabilizing emotions and physically relaxing the brain. Meanwhile, Raga by Ravi triggers a mix of theta and alpha waves, acting as a profound mechanism for stress relief and emotional grounding.
The implications of this are absolutely staggering, because guys, these aren't just subjective, self-reported feelings anymore. Based entirely on the musical biomarkers, meaning your EEG brainwaves and bioenergy field shifts, these artificial neural networks can predict your exact state of relaxation, focus, or stress relief, with roughly 90 to 93% accuracy. The machines have validated that raga therapy physically alters our neurophysiology in highly specific, completely measurable ways. This incredibly high-tech investigation brings us full circle. As noted in the conclusion of one of our key sources, it proves exactly what ancient Indian texts claimed millennia ago. The emotional power of a raga is not just a theoretical concept or some cultural myth. The principles inherent in these tonal configurations are a practical, biological reality. They actively rewrite our brainwaves, systematically creating that blissful, aesthetic experience known as rasa. So now that we can successfully decode the emotional grammar of a raga, and we can predict its exact impact on human brainwaves using neural networks, it leaves us with one incredibly fascinating question to ponder. What does the future of mental health treatment actually look like? Imagine a world where AI doesn't just play a song you like, but dynamically generates a personalized, non-invasive neurotherapy session, perfectly tuned to lower your anxiety or boost your focus in real time. The math and the magic of music are finally speaking the exact same language. Thank you so much for joining me on this explainer, and I really hope it leaves you listening to your favorite music just a little differently today.